In this video, I'm going to talk about powers of complex numbers, and I'm going to work up to a really important result about complex numbers. We're going to start with z here. I've defined z to be 1 plus root 3i. You should be in the habit of, when you see a complex number, just doing a quick sketch of where that will be in the complex plane. So we've got z at 1 along and root 3 up. Let's put it about there. 1 plus root 3i. There. I want you to do some calculations yourself now. Given that that is z, what is z squared and z cubed? Pause the video now and work those out. All right, hopefully you've done that. My turn. I'm going to do my workings over here. Z squared, I'm going to take that x plus iy form and expand the brackets. So the real bits first, we've got 1 times 1, and I times I is minus 1. Root 3 times root 3 is 3, so we've got 1 minus 3 is negative 2. And the imaginary bits, we've got plus root 3i plus root 3i. Plus 2 root 3i. So that is what z squared is. Negative 2 plus 2 root 3i. Cross fingers, you got that yourself. So that is over here. It looks like it's sort of double it in the direction over there. Z cubed. Z cubed, if that was z squared, then z cubed, we're going to take z squared and times it by z again. 1 plus root 3i, and expand these brackets. We've got negative 2, I times I is minus 1, root 3 times root 3 is 3, so we've got minus 2 minus 6. And the imaginary bits, we've got plus 2 root 3i, minus 2 root 3i. So they cancel out. It's just on the real axis, the negative real axis over here. Z cubed is over there. And it's minus 8. Let's write that in there. Beautiful. Hopefully from that, you've noticed or remembered what's going on with the argument there. When we multiply two complex numbers together, their arguments add together and their moduli multiply together. So let's be specific with this. What is the argument of z? We could do inverse tan of root 3 over 1, opposite over adjacent. But a tip here, whenever you see root 3 in a question about complex numbers, it's often to do with an equilateral triangle, because root 3 comes out in the height of an equilateral triangle. This here is an equilateral triangle, if we were to fill it in down there, with pi over 3 there and a modulus of 2. If you do a lot of these, you become accustomed with that sort of thing, but you can plug it into your calculator to check anyway. So, when we've multiplied by itself, its argument has added to itself, so that becomes another pi by 3, 2 pi by 3 in total, and another another pi by 3 over here. I'm getting too excited. To give 3 pi by 3 in total, which equals pi, which is why it ends up on the axis going that way. And the moduli, 2 squared becomes 4 and 2 cubed becomes 8 along that way. That's how those have turned out. Now, I'd like you to think about that when doing the next one, because I'm going to jump ahead a little bit, and I want you to try to figure out what z to the power of 10 is. Pause the video now and try to figure that out. All right. hopefully you've had a good think about what we just said, or thought back to a previous video about different forms of a complex number, how this x plus iy form, it's often more useful to write it in the exponential form or the cos theta plus I sine theta form. So let's do that, or at least think about the modulus and argument first. The modulus, slightly easier. The modulus of z to the 10 is going to be 2 to the power of 10. 2 to the power of 10, which is 1024. And the argument of z to the 10 is going to be 10 lots of the argument of z. 10 pi by 3, let's figure out where that would be. Well, 10 pi by 3 is like 3 whole pies plus another one, plus another pi by 3. And every time we travel 2 pi around, we end up in the same place. So this is equivalent to, I'm going to use this because these two values aren't equal, but this symbol can mean this. This is equivalent to just 1 lot of pi plus pi by 3, so 4 pi by 3. So z to the 10 we can write as I'm going to use the r cos theta plus I sine theta form. We're going to write as 1024 times cos of 4 pi by 3 plus I sine 4 pi by 3. If we plug that into our calculator to get it as some numbers not writing cos or sine, so cos of 4 pi by 3 is minus a half. How nice is that? Minus a half plus, change that to sine, minus root 3 over 2. Minus root 3 over 2 I. Let's expand that out because we can do this times a half is 512. So that's negative 512 minus 512 lots of root 3i. Beautiful, beautiful, beautiful. I quite want to check that and show you what's going on in Geogebra. So let's skip over here. I have here Z drawn out there in blue and W plotting Z to the power of n. So one that we missed off our list was the one before Z. We could write Z to the power of 0, and any number to the power of 0 is the number 1. This will let me drag this up and see where we end up. So Z to the power of 1 is Z. Z squared is there at 2 plus, that looks like 2 lots of root 3. See what, this will be easier if we see where W's been. So let's click that. Z squared is there. Z cubed we saw was negative 8. And I think we're going to need to zoom out to see Z to the power 10. So let's zoom, 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 zoom. Zoom, 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 zoom. That should be enough. That should be enough. Okay, let's play it and see if I can stop it on 10. It's coming. It's flashing at every integer power there. 8, 9, 10. Oh, that was so good. So Z to the power 10, negative 512, and what is 512 times root 3? 512 times the square root of 3 is exactly that. Beautiful. I'm well happy with that. We can see here from the picture how doing the powers of Z, it's spiraling because the argument is adding on to itself and it's getting further and further away from the origin exponentially, actually, because it's 2 to the power of, the modulus is 2 to the power of n in this case. So it's spiraling outwards and outwards and outwards, and ending up at so to the power of 10 there. Oh, I'm well happy I could stop that exactly on 10. Well done me. Okay, so that's for that complex number there. We found a way of finding any integer power of it, and I could let it keep going up and up and up and up and up and up and find the bigger ones if I wanted to. I'm going to write out what we just did in a formula. What did we do? What did we do? We said that if we had a complex number, say r cos theta plus I sine theta, and we raised it to the power of n, then that is the same as the modulus is raised to the power of 10, and in here, the argument is timesed by n. That's what we just did. Now, if I was to write that out again, without the r to the power of n, just to make it a little bit neater, and just focus on the argument bits, now equals cos of n theta plus I sine of n theta. That there, that statement that we just reasoned through, is a beautiful relationship between our trigonometric functions and complex numbers. It is called de Moivre's formula, or de Moivre's theorem. De Moivre's theorem. Named after a French mathematician, Abraham de Moivre. I've got him over here on Wikipedia, who was alive in the 17th century. And apparently, according to Wikipedia, also a friend of Isaac Newton. You can look that up yourself if you're interested in learning about de Moivre. Now, de Moivre's theorem here, I'm going to show you one other thing that we can do with it. We've also seen how it's useful in finding powers of specific complex numbers. But we can also put it to use to prove some lovely identities about trig functions. I'm going to pick a specific value of n. Let's stick with squared right now and write cos theta plus I sine theta squared is cos of 2 theta plus I sine of 2 theta. Now, there's something else we can do with this. We can expand this left-hand side as though it was just any other bracket that we were expanding. Let's do that. So that is cos theta plus I sine theta times cos theta plus I sine theta. Let's do the real bits first, as we did before. We've got cos squared, I times I is -1, cos squared minus sine squared, cos squared theta minus sine squared theta. And then the imaginary bits, we've got sine theta times cos theta plus sine theta times cos theta. So we've got plus 2 cos theta sine theta I. And when we've got complex numbers that are the same, we can equate real parts and imaginary parts. So I just equate the real parts here. This is telling me that cos of 2 theta is the same as cos squared theta minus sine squared theta. And if I equate the imaginary parts, we've got sine of 2 theta is 2 lots of cos theta sine theta. Now just dwell for a moment on what they mean. We haven't got any imaginary numbers in here anymore. We got rid of those when we equated the real parts and the imaginary parts. Theta is just any real number because it can define that angle, and that angle could be positive or negative, it could go any way, it could be as big as we want. And we've got this identity that holds for all values of theta, so really we could write that says if we times it by 2 inside the cos, then that's the same as this. Do you even believe that? That's come out of de Moivre's theorem, but do you even believe that? I'm going to get onto Desi, just to try and make you believe it. Oh, come on. Where I've plotted cos of 2 theta and cos of 2x and cos squared x minus sine squared x. And just look, they're exactly on top of each other. They're exactly the same. Let's just try it for sine as well. Sine of 2x looks like the green one there. Let's get rid of the cos's. And what was it? 2 cos x sine x. And they're exactly the same. They're exactly the same. These identities, we label these ones in particular the double angle formulas that help us to relate different values of sine and cos. And we've proved them by going via complex numbers, even though there are no complex numbers necessary in these little formulas. That's mad. You can hopefully see how you'd be able to do similar with cos of 3 theta and find a formula in here by expanding out that cubed and then equating real and imaginary parts. Brilliant. I've enjoyed that. I think this is a beautiful theorem that connects complex numbers with trig values that comes out of an intuitive sense of what happens with complex numbers when we raise them to different powers. Good luck with your own practice with it.